Alright, what do I want to, how do I want to approach this? What are you doing?
Nothing.
Let's dive in and start working a problem. This is going to be your crash course, man, in kinetics. Get out your problem packet.
Sorry.
Get out your problem packet. It says problems at the top. Problem 84. Problem 84, because this encompasses just about everything. It doesn't get into the integrated rate law, but it does use the differential rate law and the reaction mechanism. So I'm going to be going up to the board file, so you may have to. I have to go to the board. If I work problems, thinking them out loud, y'all write things down. Even after I tell you, I'd write this down if I were you.
Why would you do that to us? I don't remember how to do ugly algebra.
What, you have to do ugly algebra on these? Yeah, you do.
Yeah, you do.
I don't understand. What do you mean, like, ugly
There's such a
algebra?
thing as ugly algebra.
You'll find out very, very soon.
You take the rate of 1 and divide it by the rate of an... Let's look at problem 84. Let's look at what information is being given to us and what we have to do with it. Gives us a hypothetical chemical reaction. It gives us the equation, 2x plus y is equal to, or yield z. It gives us initial rate data in the data table, all measurements at the same temperature, so you know that temperature is not a factor in the rate of the reaction. It gives us the initial rate of formation of the product, and you can see the units associated with it there. It's molarity per unit time, and in this case it's seconds, so molarity per second. And then it gives us the initial concentration of our X and our initial concentration of our Y. Now, for the differential rate law, you're going to look at data information. You're going to be looking at how the concentration of one affects the rate, or how quickly the reaction proceeds, and comparing it to how the concentration of the other reactant influences the rate. So, this is where you have to look at the concentration of X, hold it steady. So pick two reactions or two equations there where X does not change. In which experiments would that be?
The first and second one.
That's 2 and 3.
2 and 3. 2 and 3, X doesn't change.
84.
Oh.
Right?
Right.
Yeah.
So between experiment 2 and experiment 3, 0.4 and 0.4. So X doesn't change. Now look at experiment 2 and 3 as far as the concentration of Y. What has happened?
It doubled.
It has doubled. So the concentration of Y is doubling. At the same time, what has happened to the rate of the reaction?
It doubled.
It doubles, okay? So it's at a 1-to-1 relationship.
Yes.
The concentration of 1 has doubled, the rate has doubled. That's a 1-to-1. So we say that as far as our concentration of Y is concerned, it's first order. That means for every change in Y, we're going to see a corresponding change in the rate, or how fast the reaction is proceeding.
Write that down.
Okay? So we're building our rate expression. We're building it. Now, the second part, and this may be where the algebra is coming in.
Yeah, it's for X.
Okay. Find a place where Y stays the same between two expressions, or two reactions.
And they don't have to be double. It can be anything. Triple, variable.
Is there a scenario where Y doesn't change?
No.
No.
No. So this is where we have to get into what is called ugly algebra. And it's not ugly, really. It just means you have to do an extra step. You can't use logic. You now have to use math. Okay?
You can cancel out Y, though, because it's 1, right?
Mm-hmm.
Okay.
Okay, so what you have to do here is pick two. So let's just pick the first two because it really doesn't matter, right?
Mm-hmm.
So in trying to determine the concentration of X, this is what we're trying to do. We pick the first two experiments. So we have rate of the second divided by the rate of the first is equal to.
Concentration X1.
Oh, are you doing it for me? Good.
Alright, it's 2. I don't know.
Right when you divide?
You're going to divide.
1.4 divided times that.
Oh, I don't have my data table in front of me anymore. Okay, we need to set this equal to something. What are we saying?
Concentration of X2 over concentration of
So
X1
X2,
over X1.
and then this would be,
Y2, Y1. Oh wait, what about K? Did you put that in there?
oh, we did put in K.
Oh, sorry.
Oh, but all we're looking for is our concentration values, right? We don't know
Well,
what K
yeah,
is.
I guess so.
So we're not really factoring in K at this time. We're trying to see the relationship between this half of the equation and this half of the equation. Okay? You can pick any two reactions just as long as you have them set up in the same ratio. So now, what's rate 2?
1.4 times 10 to the negative third.
And rate 1?
7.0 times 10 to the negative fourth.
I should just listen to what you're telling me as opposed to trying to fill it in. Okay?
Rate 0.4 over 0.2. And Y is 0.1 and 0.2.
Okay, so what are we actually solving for here if we set it up in this way?
No, the y would be 0.2 over 0.1, right?
Yeah, 0.2 over 0.1 because, 1/2 and 2 aren't the same thing.
So it's 0.2, 0.1.
Uh-huh.
So what are we solving for? Because we have all of our variables filled in.
We'd be solving for K, right?
That.
No, you're solving for the
What X?
exponent. Not exponent.
We're solving for this, which we call, which is called A, right?
Uh-huh.
We'll call this B because we already solved what it was, right?
Right.
It didn't matter. Our unknown equation is x plus y equals z. And so what we're actually solving for is the constant up here. We solve for this constant by manipulating the table, by just seeing the relationship between the change in the concentration and the change in the rate. We can't do that with x, so what we have to do instead is solve for this unknown. So, if this is raised to the first, this is raised to the first, right?
Right.
So now we're solving for, what is this?
1.
Okay, you've already solved it?
No, 0.4 over 0.2 is... Never mind, we're solving for that.
Okay,
Yeah.
okay. So now it just becomes a mathematical problem where you're solving for the exponent. So this is where you have to have your calculators. This is often going to show up as part 2, or question number 2 in a
2
problem.
equals 2 to...
No, isn't A is going to be 0, right? Because the rates combine equal 2, and the y values...
So simplify this. What is this?
2.
2, and the y's are 2. So that simplifies to 1, so the exponent has to be 0.
And this simplifies to
2.
2.
2? To the A?
Uh-huh.
So A equals 0?
Yes,
So then this factor goes away, and so our rate is equal to y to the
K.
first.
No, oh, yeah. Sorry.
K. Thank you. Now we insert our K.
Maybe that's what I've been doing wrong, because I've just, if it's in the first order, I've just been getting rid of the number. Like for the Y.
Yeah,
Maybe that's why I keep missing these.
if this is 0 order, you can do that, because then everything becomes to 1.
First, or just 1. It's just
1.
Yeah.
So the answer to A is rate equals K times concentration of Y raised to the first power. And you don't have to put to the first power, but...
And if it's if it's second order, you put squared. Like X squared.
Okay? So I mean, it's not difficult to do with a calculator. If you don't have a calculator, it's a little bit more challenging to do. So just
Well, not really. I mean, 0.7 times 10 to the third.
right. I mean, it's not that difficult. You should be able to manipulate this without. But again, when you're thinking about what kinds of math problems you're going to see on the multiple choice or in parts or problems 5 and 6 on the exam where you don't have a calculator, you're going to think easy. It's got to be easy math. Okay. So that's the rate expression. Calculate the specific rate constant, that's K. Whenever you see a constant in chemistry, we're thinking K. So calculate the rate constant for this reaction specified as heating. Now you pick one reaction and substitute it in. I'm going to pick reaction 1 simply because it's the first one there.
is equal to 0.007. And then its units would be per second.
No,
A one.
Yes.
yeah.
Yes.
Well, isn't that the same as hertz though?
Yes. And what is the definition of hertz?
Now.
Oh, it's like it's the number of waves that pass a certain point in a second.
Per unit time, per second. And so we're looking at how fast the waves progress past the point, right? So here we're looking at how fast the reaction is progressing.
Okay.
Okay? Alright, so that's 3 points. I'm sorry, that's 5 points already. 3 points for the first one, 1 point for the law, and 2 points for the methodology. Yes, 2 points for the methodology and 1 point for the law. So you only get 1 point for having that right there. So let's say you have no idea how to do it, you just write it down, you got lucky, you get a point. But if you go through and at least show a setup, you don't have to show all of the work. If you show that right there and you get this correct answer, that's 3 points. Okay? And then on the second one, it's 2 points, 1 for the answer and 1 for the unit. And if you just write it as one answer, then that's sufficient. Okay, the next one. How long does the reaction proceed to produce a concentration of Z equal to 0.2 molar if the initial reaction concentrations are 0.8 and 0.6 and 0 molar for Z initially? So what do we need to do with this?
We didn't do rice tables with.
You're not doing right tables with this.
Yeah.
You're not looking at equilibrium concentration.
Take the molar relationships.
Go to your, what order of reaction is this? I think it's on your cheat sheet. What order of reaction is this?
I guess at first, because it's the sum of all the.
The first order. So go to your cheat sheet.
Oh, so we'd use the integrated rate law
Now we're using the integrated rate law.
because it's with time.
Or do we need to use the integrated rate law?